So whether it is deep space or Earth, the environment that surrounds the semiconductor chip is dynamic. In space, radiation and extreme temperatures can cause significant changes in the behavior and reliability of the semiconductor chips, whereas on Earth, environmental factors such as temperature, humidity, and vibration can also affect the performance and reliability of the chip. In addition to that, the AI requirements are also continuously varying. With the increase in the number of sensors, the new data is being collected every day. This would mean we have new accuracy, new computation, and new latency requirements after every couple of months. This is why we need to work on designs and semiconductor chips that can adapt based on the changing surroundings and AI requirements. So in this academic style, in-depth video, I will discuss a reconfigurable CNN accelerator, which can be reconfigured in 3 operating modes: high reliability, high performance, and aging reduction mode. Without further ado, let's get into it. So, hi everyone, welcome back to another video. In this video, we are going to be discussing another paper, which is a fault-tolerant CNN accelerator with reconfigurable capabilities. So last time we discussed shared layers methodology, and it was this paper towards reconfigurable CNN accelerator for FPGA implementation. This was that fundamental idea which we take as a baseline, and we will build reconfigurable accelerators on top of it. And this is the current paper which we are going to be discussing today for FPGA implementation of a fault-tolerant fused and branched CNN accelerator with reconfigurable capabilities. You can also just Google it, you will be able to find the paper, and also this is the link. So yeah, this is the outline of the video. Let's have a look why we are doing it, what are the challenges do we face, and what is really the motivation behind all of this work. So whether we observe it or not, we are surrounded by AI assisted technologies. And it has been an integral part of our lives, from Netflix movie recommendation to online ID verification, everything involves the use of AI algorithms, all the chat GPTs and Amazon Alexas and all of those things are using some sort of AI in one form or the other. So because of the state-of-the-art results of AI in the prediction, classification, and natural language processing, it's also being heavily used in safety critical applications as well. For example, automated driving or space missions or future 6G communication infrastructure. The future 6G communication infrastructure system will serve as the central nervous system of the digital economy. And this means that the requirement for reliability, resiliency, and fault tolerance will increase in the future because everything will be hyper connected. It will act as a central nervous system of the digital economy, right? What challenges do we face currently when it comes to AI implementation on hardware for safety critical applications? Neural network models are going to be implemented on hardware, but the requirements of AI are continuously varying. The number of sensors are continuously increasing, and with that, the new data is being collected every day. This would mean that you now have a new accuracy, computation, and latency requirements after every couple of months. And this change in the AI application requirements directly impact the hardware resource utilization and the power or energy consumption. And as we know that hardware is prone to errors, the downsizing of the transistors results in increase in the vulnerability to transient faults due to reduced threshold voltages and narrower noise margins. Imagine this self-driving car scenario where you have a fault-free execution. In this scenario, the car will apply brakes because it is detecting a truck. In an erroneous execution, in an execution where the hardware is faulty due to either hard errors or soft errors, there is a misclassification. And in this case, brakes may not be applied. And this can lead to a huge loss for humanity and financial loss as well. I mean, this is happening on Earth, but For example, the space environment is even more harsh as compared to the Earth. There are high energy particles in space which can strike the chip, which can cause us soft errors. Therefore, we have to make our hardware design safe enough to run AI algorithms for safety critical applications. And that's why the hardware should be thoroughly verified. So if we can broadly classify the challenges, we can map it to three broader category of challenges. First is the efficient mapping of AI models for safety critical application, ensuring the reliability so that our hardware can be used for safety critical application. And then the reconfigurable aspect or the self-adaptive aspect, so that our architecture reconfigure itself based on the changing AI requirements or the based on the changing environment around itself. For example, in space, the environment changes so rapidly. So self-adaptive nature of accelerators or microprocessors can really help us optimize for reliability and performance. As I said, the shared layers methodology, which we have discussed in the last video, but I will also go through it briefly in this video as well. And then using this methodology, we will extend it towards fault-tolerant, fused and branched CNN accelerator with reconfigurable capabilities. So the shared layers methodology is basically aiming to solve the challenge of efficient mapping of AI models. Because this approach means that we are executing multiple tasks from different modalities on one accelerator. This is an efficient way of implementing multiple tasks on one single accelerator, which reduces a lot of hardware resources and also energy. And then extending this shared layers approach, we propose fault tolerant, fused, and branched CNN accelerator, which can reconfigure itself in three operating modes, which are fault tolerant, high performance, and de-stress mode. And this contribution aims to solve the reliability challenge that we have for safety critical application, and also adds reconfigurability and self-adaptiveness within the architecture. And this helps us to adapt the processing system as per the application requirements. If you need high reliability, you can switch to fault tolerant mode. But if the requirement is for high performance, you can reconfigure it quickly in real time and to support high performance mode. And if you would like to have low power, or if you would like to reduce the aging, you can go towards the de-stress mode, and this can all happen in real time. And then we will also discuss comprehensive experimental results for all three operating modes as well. So first, let's have a look at the shared layers methodology. So traditionally, if you would like to implement these three tasks, you would be needing separate accelerators. And this is exactly what we are targeting in shared layers methodology. We are saying instead of using three accelerators, you can use just one accelerator. And how does this work? Let's have a look at it. So if you have a look at the CNN architecture, convolutional neural networks, the way it works is that the lower layers of the convolutional neural network, or the initial layers of the convolutional neural network, learns the low level features like edges, curves, and blobs. And as you go deeper in the convolutional neural network, your network start to learn more abstract high level features, right? And a lot of the image related inputs, a lot of the patterns that we have from radar or the camera, the low level features are the same, right? The high level features can be different and may be different. For example, this is a SVHN dataset, which are numbers, but in radars, the high level feature is a totally different thing. So we use this approach to train one CNN model on all the three tasks. And this means that when you are sharing layers, you are sharing the processing elements. And this means you are saving hardware resources. And this also leads to saving in the power consumption. So here you have three accelerators for three different tasks. And now here in this fused CNN architecture, Based on shared layers methodology, you can execute multiple tasks in a time division multiplex manner on one single accelerator, which would be really hardware efficient and power efficient. And this approach can also be combined with other model compression methods, for example, quantization and pruning. So our approach complements the existing model compression approaches as well. And based on shared layer methodology, we have comprehensively tested two different architectures. One is the fused one and one is the branched one. In fused model, all the tasks share all the layers of the neural network. Only at the output layer here, the neurons for each task are different. It has a single output layer consisting of 26 classes, but each task would be having separate neurons. Whereas in branch model, there are task specific branches which only share particular layers. In branch architectures, there are certain benefits. For example, in case of a fault, there can be task isolation, so that it does not affect the entire network. If we are implementing it on FPGA, we can do task specific bit stream reconfiguration. So we don't have to reconfigure the whole network. We can just focus on a particular branch and then we can reconfigure it. We can do selective replication of only specific layers. For example, if there is a task which requires high reliability, we can only replicate or add redundancy for that specific task. In short, we can do selective hardening in a branch architecture, which is a more hardware efficient way of adding fault tolerance or increasing reliability. Addition of subtasks. One task can have multiple subtasks. For example, task 3, we can detect digit as well, and we can also detect the color of that input. And also one more thing, in branch architecture, we can do task specific training to increase the accuracy of a specific task. In the fused one, because we are training it together and because all the tasks share all the layers, it is very hard to sometimes achieve good accuracy for all the tasks. While in branch architecture, you can do task specific training as well. You can add more layers to a certain branch to achieve more accuracy. These are the implementation results for fused and branch models with pruning and quantization as well. So these are the 4 fused models. One is the baseline model, which is not quantized and not pruned. Then we just prune the model and then we just quantize the model. And in this case, we have added quantization and pruning together. And this is the branch version along with quantization and pruning. And you can see that the more we are seeing the reduction in the power, right? As this is the most optimized fused model, which is also quantized and pruned, you can see that this is consuming the least amount of power. And between fused and branch model, you can see that there is a slight difference in the accuracy. Branch models gives you slightly better accuracy with slightly higher power consumption and with slightly increase in the hardware resource utilization, but it gives you reliability advantages which we have discussed before. In general, on one accelerator, you can see that for all the tasks, we are achieving quite good accuracy. On average, we are achieving 90% accuracy for all 3 tasks. You can also have a look at the hardware resource utilization. The more you're optimizing the model, the more hardware resource utilizations are decreasing, and also the power is decreasing in the similar way. So this was shared layers methodology, which was an efficient way of implementing multiple tasks from multiple modalities on one single accelerator. And these 3 tasks execute on a single accelerator in a time division multiplex manner. Now let's have a look at the other approach, which is fault tolerant fused and branch accelerator with reconfigurable capabilities. We extend this approach further, and this means we are now ensuring reliability as well, and we are also adding reconfigurability. So this was the architecture which did not have any redundancy. By default, one accelerator is sufficient to perform 3 tasks. But with redundant accelerators, it is possible to execute tasks in fault tolerant mode, high performance mode, and de-stress mode. This approach of having different operating modes is typically seen for multi-core processors, but this approach has not been explored so far for CNN accelerators. This makes our study unique as well. So because we have different operating modes, we can have a trade-off between reliability, power consumption, and high performance. Let's have a look at it. How three tasks will perform in fault-tolerant mode, and how they are going to be performing in high performance mode, and how they will be executing in de-stress mode. In fault tolerant mode, we have three accelerators and all three tasks will be executed on all three accelerators. This means that we are operating it in TMR mode. And this means that even in the presence of fault, our system will continue to work. This is a fail operational mode. Like this, the tasks are being executed in parallel on all three accelerators, and at the end of it we can have a majority voter so that we can see which accelerator is faulty, and this provides us a very high reliability for all three tasks. And this is really useful for safety critical applications, for space, for automotive, and for future 6G communication infrastructure systems. The second mode is high performance mode. This means that each task will be executed on one accelerator, or in short, parallel execution. And this leads to a 2x reduction in the latency. The third is the de-stress mode, or aging aware mode. In this, only one accelerator is active at a given time, and the other two accelerators are either idle, clock gated, or black boxed in FPGA terms. In this way, you are able to reduce the dynamic power of the design. So only one accelerator is active and it is executing this task, and the other two are being put in the idle mode. This leads to reduction in the aging. This also leads to reduction in the power consumption. For example, three tasks are executed on one single accelerator while the other two are idle or clock gated or in black box. So these are the implementation results when our accelerators are executing in fault tolerant mode. In case of a fault tolerant mode, we have performed a comprehensive fault injection analysis. In fuse model, this is the total number of faults that were injected at the RTL level. And in branch model, this is the total number of faults which were injected. And we have considered three fault models: single event transients, single event upsets, and multi-bit upsets. So for single event transient, we have considered 1000 picosecond of pulse width. So this pulse width is higher. Normally the pulse width for single event transient is less than 1000 picosecond, but we have considered as the worst case scenario because sometimes pulse broadening happens. So generally what we have observed is that branch model is slightly more resilient, roughly 2 to 3.6% than the fuse model because of its branch architecture. So what it is showing here, in case of SETs, in fuse model, 0.977% of the faults propagate to the output, while in case of branch model, 0.79% of the faults led to the output, leading to incorrect results. So this means that branch model is slightly more resilient as compared to fuse model. So single event upset. So in case of single event upsets, 16.76% of faults led to incorrect results for fused and 14.6% for branch. And in case of multi-bit upsets, 30.34 faults led to the output of fuse model and 26.75% in branch model. These are the results for faults that will lead to the output for a single accelerator, because we are trying to understand the vulnerability of one single accelerator. But in DMR configuration, if you use two accelerators, you will be able to detect all of these faults. And with TMR configuration with three accelerators, we will be able to also correct all of these faults. If the percentage is higher for multi-bit upsets, it can still be corrected by TMR configuration. So the fourth fault model is fault injection directly in the FPGA bit stream, because here we were doing fault injection at the RTL level, but here we are doing fault injection directly in the configuration bit stream of the FPGAs. So let's have a look at it in the next slide. How can we sort of emulate this behavior and how can we recover from this fault? So we have to first understand that ASICs are slightly different as compared to FPGA fabric. So in FPGAs, if a fault is happening in the configuration bit stream of the FPGA, it has an permanent impact, because configuration memory is like a memory, and if an FPGA fabric is huge, so if a fault is happening there, it leads to a permanent impact. And in that case, fault mitigation happens usually by reprogramming the bit stream, right? But in case of ASICs, like you don't have like lookup tables generally. So the impact of a single event upset is different. For example, if there is an AND gate, this AND gate is implemented on a lookup table in an FPGA. So here, if the fault is happening in the configuration bit stream, it has a permanent impact. But here, it will not be permanent. There will be single event upset if it gets latched, but it can be overwritten by the next load. So in FPGAs, fault injection is performed on randomly selected 4,000 different essential bits, and we have injected the fault using SEM IP core of the Xilinx. And SEM IP core is used to inject the fault as well, but this IP also helps us detecting or correcting the fault in the configuration bit stream as well. And the latency to detect and correct varies a lot, from 3.14 millisecond to 48.98 millisecond. It depends where the fault location is on the FPGA fabric and the clock frequency at which you're running your design. So based on these two factors, the correction and detection latency can be different. So this SEM IP core actually complements our DMR and TMR based design, which was this one, which we discussed in the last slide. So in short, what I'm trying to say is you can use SEM IP core and it can complement your DMR and TMR based design, and it gives you a comprehensive safety, right? This combination would mean for these three faults, this architecture would be providing you high reliability, while for single event upsets in the configuration bit stream, your SCM IP core would be providing you high reliability. That means detection and correction mechanism. So they can, work together to give you highest reliability possible. Now let's talk about high performance mode. And as we said, in high performance mode, all three tasks are executed on three accelerators in a parallel fashion, right? Which leads to reduction in the overall latency by 2x, which is 5.21 microsecond per sample. And if you use just one, it will be around 15 point something, right? 15.63, I think. It will be around 15.63 if you use just one accelerator. But when you're parallelizing it, you can get the task done in 5.21 microsecond. And this leads to having approximately 0.79 TOPS compute power in high performance mode. And interestingly, if you're using high performance, this also means you are saving energy because of shorter overall latency. We will look into these results later in the table. De-stress mode. So de-stress is an aging aware mode. And aging in semiconductor devices, it refers to the gradual degradation of the circuit performance over time, right? Because the threshold voltage of the transistor increases, and because of that, it leads to decrease in the carrier mobility. And aging is influenced by various factors such as supply voltage, switching activity, temperature, transistor stress duration. So we are trying to reduce the aging by controlling this switching activity factor. And when you are reducing the switching activity, and the thing is, the power consumption due to the switching activity of the circuit is called as dynamic power. So we want to reduce the dynamic power as much as possible so that we can reduce the aging which is being caused due to the switching activity of the circuit. And this is why we put the two accelerators in idle or clock gated or in black box mode, and we are using only one accelerator, and this means that we are reducing the aging. So there are also different ways of making these two accelerators idle. One is clock gating way and the other is partial reconfiguration way. The clock gating way, in this case, what you are doing is you are blocking the clock of the accelerators. So you're not supplying them any input. You're putting them in reset. You're not supplying any clock, right? So in this way, we can, make the switching activity as low as possible. But the thing is, even in that scenario, clock gating still use 34.5% of the dynamic power, which causes aging. There is another way, partial reconfiguration way, which is erased bit stream. So we put the accelerator idle by totally erasing that part of the fabric. We don't program it at all. We only program that region of the FPGA where we want to execute all three tasks, right? So the other two areas of accelerator, has been put into, let's say, have been considered as black boxes. There is no bit stream being programmed here, and this can lead to maximum savings in the dynamic power consumption. And after a given time, we can program this central part of the fabric while making the other two as black boxes, so that we can evenly distribute the stress across all three accelerators. So these are the experimental results for high performance, for fault tolerance, and de-stress. We are comparing these three modes for latency, power, energy, and performance. De-stress, we are considering two approaches. The clock gated approach, we have also have a look at the power consumption, while also we had a look at the power consumption in partial reconfiguration. We can see that even though the accelerator 2 and 3 are in idle mode, it is still consuming 0.393 watt power, even in idle mode, right? And this means that this is contributing to the aging. While in partial reconfiguration mode, there is no bit stream at all at that specific fabric. So this means that at least we are not having any dynamic power consumption. This power is basically dynamic power, which happens due to switching activity of the transistor. And this is the energy. You can see that the high performance mode has the lowest energy because it is completing its task in the lowest time. And also the energy values are approximately the same in fault tolerant mode for all three accelerators, because all three accelerators are basically executing the same task, right? So that's why it has a similar energy values. So the comprehensive analysis of this table is also provided in the paper, in case if you would like to, read it and understand it in even more depth. So in this table, we are comparing our work with previous fault-tolerant studies. Conceptually, our work is different as compared to other studies. So you can see that we offer a different perspective around reconfigurability in DNN accelerators. In addition to that, we also offer deeper insights into 4 different fault models, and our results also involve multiple tasks and multiple modalities as well, right? While you won't find all of these things in other studies. This is also another comparison, and one of the major difference between our results is that we injected fault in the complete accelerator architecture of the neural network, and we also injected at the RTL level and also directly in the configuration memory of the FPGA. While other studies, majority of the time, only injecting faults in the CNN parameters, which are the weights of the neural network, and they are completely ignoring the architecture of the neural network. And a lot of them do it at the software level. And we know that the software level neural network model is totally different as compared to the actual RTL based neural network model, right? Of course, software is faster and software gives you good high level estimation of fault injection analysis. But when it comes to more realistic results, the more you go down towards hardware, the more realistic it becomes. But hardware fault injection can be time consuming, but it gives you it gives you realistic results. So we have performed fault injection at the RTL level and directly in the FPGA configuration bit stream. So that's what makes this study unique as compared to others. And now in this table, we have quantitatively analyze our results as compared to FPGA based studies and also ASIC based studies as well. You can see that our results have been competitive. While the other studies are using only one datasets or mostly datasets from the similar modalities, we are using 3 dataset or 3 tasks from 2 different sensor modalities, radar and camera. You can also have a look at the power, that how much reduced power we have as compared to the other studies. So let's summarize this video as well. So we discussed the motivation and challenges in the beginning, and we discussed majorly 2 important research contributions in this video: the shared layers methodology and extending this methodology to support fault tolerance and making it reconfigurable. We have performed comprehensive comparison, conceptually and quantitatively with several other state-of-the-art studies, and we can say that our results have been competitive. What we can do in future, we can extend the shared layer approach with additional sensor methodologies. For example, audio signals also have a certain map. They have a certain pattern, right? These signals can also be recognized using CNN. So maybe we can also include audio signals to make it, three modalities: radar, audio, and camera. All three of them, all four tasks getting classified by one single accelerator. This is something which we can look in the future. And the other important thing that is happening in our group is the development towards fully reconfigurable AI processing system. And this is something which we will also continue to discuss in future videos, that how we are thinking in terms of fully reconfigurable processing system, and how these two approaches can be some of the important component of this processing system. So that's it from this video. Thank you so very much for your time. So please like this video and also subscribe to the channel. It will really motivate us to continue to make such in-depth videos. Also, if you would like to get connected with me, you can scan this QR code and we can get connected on LinkedIn. Thank you very much, and I'll see you in the next one.